Last time we were discussing the format of a float in MIPS, and this is the format. It is 8 bits for the power, for the exponent, 23 bits for the decimal, for things after the decimal point. It's not really a decimal point, it's a binary point, but because this is a binary number after the binary point.
We can't see your screen.
Oh, sorry, my fault. Thank you for telling me that. No, that's not what I want. Okay. Now you can see my screen, correct?
Yes.
Great. And I see I have a few more people in the course, so we have a few more people. 6. Okay, good. Whoever is not here should watch the video that I will post of this class. Again, for those who didn't hear my long introduction, you need to tell me whether you prefer to continue Zoom or if you want to do video.
Where do we tell you that?
I gave a long introduction about how I see that nobody is reviewing the videos, and yet people are complaining that they're falling behind. The videos should be reviewed. The material, the slides are posted. There is a plethora of knowledge on the internet. If any subject is not understood, you can seek out knowledge and you shall find. If you send me an email, I will answer you if you have a particular question. If you want me to review something, well, I can review it because I have the video. You can watch it. You can review it yourself at your own speed, at your own time.
So where did you say, though, we should tell you whether we prefer Zoom or videos? I
announced that in class last time. One of the students said that he would take a survey and send it to me. He never sent me anything. But I asked if people should write to me, and nobody wrote to me. And the person who made the survey, if he didn't send it to me. So I have no information from you as to what your preferences are. Please send me information. My email is targilimdanzig@gmail.com. And you guys need to not fall behind, and you have plenty of ways of not falling behind. Watching the videos that I post, reading my slides, doing the homework is also the review of the material that we have done. And if you have particular questions, you should certainly not hesitate to write to me and I will answer you. But there is no reason that you should fall behind. Last time we were talking about this slide, and this is the representation of a floating point in MIPS. The first digit is the sign, the next 3 digits is the exponent, and the last 23 digits are the the number after the point. And it's always of the format 1.x times 2 to the e, where e is this exponent here, 8 digits, and x is this 23 digits here. The 1 is implied, and this one is the sign. You can write it mathematically in the following way. We write -1 to the sign. Now remember, the sign, if it's 0, means any number raised to the 0 is going to be 1. So we're going to do 1 times the number, which means the number will remain positive. Notice the number, because this is -1 to the 0 will become a 1. The negative sign will be lost, and it will be a positive number. If this sign is 1, and -1 raised to the first power is -1, we'll therefore logically be multiplying this number by +1, which will by -1, which will invert and make the number into becoming negative. So we see that we can represent the number by this mathematical equation: -1 to the sign times 1 plus whatever the mantissa was, which is the 23 bits, times 2 to the exponent, which is the 8 bits. And in the example that we did last time, we would get -1 to this 0.06640625 times 2 to the negative 110. We did that last time. This is, now we're going to talk about floating point arithmetic. If somebody stopped me if we did this last time, I don't think we did this last time.
No, we did not.
Good. So let us continue here. First, I'm going to explain to you how math works. And then we'll see how, with decimal numbers, then we'll see how it works with binary numbers. And we'll see that it is exactly the same. So as long as you remember your decimal math, you'll know your binary math. This is a decimal number. It is 500, base 10. This is another decimal number, 50,000, base 10. If you add them together, you'll get 50,500, which could be written in another way. If we wrote it in scientific notation, we could write it like this: 5.05 times 10 to the fourth. 10 to the fourth is 10,000. If we take this and multiply it by 10,000, we'll get 50,500. Now, let's show something. We can also write this 500 this way: 5 times 10 to the squared, which means 5 times 100. That's 500. Plus 5 times 10,000. 5 to the 10th, 5 times 10 to the fourth is 10,000 times 5 is 50,000. That's 500 plus 50,000. And that equals, well, look what we're going to do. Before we get to the conclusion, which is the same conclusion that we should have over here, the same sum, before we get there, we're going to take an intermediate step, and we're going to say, well, how do I add these two numbers? Their bases are the same, but their powers are different. Well, the only way we can add them without, leaving them in scientific notation is to equate their exponents. So that means we'll raise the lower one up to the level of the second of the highest one. This would be true if we had 10 numbers. We would take the highest power and rewrite it. So we can rewrite 5 times 10 to the squared to be 0.05 times 10 to the fourth. Because if we move the decimal point 1, 2 spaces, we'll get 0.5. And since we moved it 2 places, we're going to have to raise the power to 2 more places. So that'll be, instead of 2, it'll be 4. So if now we've equated them, they're both 2 numbers times 10 to the fourth. We simply add them. We do 5.05. And that is the same solution we got before. So now we have a methodology of adding numbers that are in scientific notation. And we've shown that it works. We haven't proven mathematically that it works, but we've demonstrated by example that it seems to work. We therefore raise the power. So that's what I said. We raise the power of the smaller two number. So let's do an example in binary. So if we have this number, 11.1, that's strictly speaking, that's not scientific notation because there's 2 digits to the left of the point. But it is in similar to scientific notation. 11.1 times 2 to the fourth. And we want to add it to 0.11 times 2 to the fifth. So we'd have to raise this one to the 5th power. So so this number 11.1 will become, the point will move over 1, and it'll be 1.11 times 2 to the 5th. We've now equated their powers. So then we'll get the following little equation over here: 1.11 times 2 to the 5th, which is this number, plus the original number that we had here, 0.11 times 2 to the 5th. And when we add them, we'll say 1 plus 1 is 0, carry the 1. 1 plus 1 plus 1 is 1, carry the 1. 1 plus 1 is 10, 10.10 times 2 to the 5th. And that is the answer.
How is 0.11 plus 0.11 10? Wouldn't that be 22?
No, we're in base 2. There's no possibility of having 22.
Oh, okay, fine. Okay, fine.
The largest digit.
No, before we're in base 10, I didn't realize we switched.
Yeah, no, that's what I said. This is base 10, and now we're going to see that the same thing works in binary. Right, following the same, it's 2 different examples. This is an example base 10, and now we're in binary. So 1 plus 1 is 0, not 2. I mean, it's 2, but it's 0, and a 1 goes over here. And then we have 3 1s, which is a 1 over here, plus a 1 over here. 1 plus 1 is 2, which is 10. So we have a methodology for adding numbers in binary, which is the same methodology that we have for adding numbers in decimal. Now let's do another example. But we'll do a full example because, well, we'll start off with decimal numbers and we'll convert them into binary numbers. We'll add them together and then we'll put them into the format of MIPS. So I have a 1 1/4, 1.25 plus 3/4. Obviously, the answer is 2. Because if you have 1 1/4 plus 3/4, you're going to have 2. But first, let's convert these numbers to binary. 1 1/4 is the same as 1.01. Because each place here is 1 over 2 to the 1. This is 1 over 2 squared. This is 1, and the next digit would be 1 over 2 to the 3rd. So a quarter is 1 over 2 squared. So it's a 1 in this column. Everyone see that?
Yeah.
Yeah, that should be a review from digital systems or wherever you learned binary math. So that's times 2 to the 0th. Why 2 to the 0th? Because it's times 1, and 2 to the 0th is 1. So this times 1 is this. And that's what I want. Now I have 0.75. 0.75, if you think about it, is a 1/4 and a half. It's a 1/4 plus a half. So this is a half, this first one, and the next one is a 1/4. So it's 0.11. Also times 2 to the 0th. Now he says, well, wait a second. This is not proper notation for MIPS because MIPS has to always start with a 1. So I'm going to have to move the binary point here to between the two ones. But if I do that, I have to reduce the power. Every time the point moves to the right, I have to reduce the power. Every time the point moves to the left, I have to increase the power. So if I move the point to the right, this is going to become times 2 to the minus 1. So now I've got two numbers in normalized form, which means 1 followed by a mantissa, followed by, a number. 1 followed by a point and then a number, times 2 to a power. Now, if I look at these two powers, I see that this is to the 0th power and this is to the first power, the negative first power. So I have to equate the powers. I have to raise this one up to this one. So if it was 2 to the 0 over here, this one has to be 2 to the 0. So I'm actually going to reverse what I just did, which is kind of weird. But this is the example. This is the example that the manager of the course chose. Doesn't really matter. So now that I have this, I got to equate the powers, which means I got to raise this from -1 to 0. Well, if I do that, if I got to do that, I got to move the point to the left. So this becomes 0.11 times 2 to the 0th. Now I have two numbers that are both at the same power. I can follow my procedure.
Do we always raise it to the greater power?
Always raise it to the greater power. Always raise it to the greater power. So yeah, you're not going to you could lower it, but remember that's what we did when we did it over here. We kind of understood that we should raise it to the power because we want to get this answer. We want to keep the answer in scientific notation. So we'll raise it. Otherwise you'll lose this point here. If you lower this to 2, if you lower this one to 2, then this would become, this is not going to work properly. You're going to end up with 500. You're going to end up with 505 times 10 to the squared. But that's not what we want. We want it with a 1 digit to the left. So we're going to always raise it. Assuming the numbers are in scientific notation, you always raise it. So since these two numbers are in scientific notation, I raise it, I get this number, and I wrote over here the math. Basically, I just take the two numbers and I say 0.11 plus 1.01, because why 1.01? Well, that's what I had over here. And why 0.11? Well, that's what I got after I raised it. And I add them together and I get 1 and 1 is 0. Carry the 1. 1 and 1 is 0. Carry the 1. 1 and 1 is 0. Carry the 1. 10.00. That's the math. I also can observe that, I mean, this is basically the same, saying this is actually, if I can express this mathematically in this way, by saying any number times 2 to the x plus any number times 2 to the same x is going to be those sum of those two numbers times 2 to the x. Well, that's what I just did over here. So we got this number, but this number is not normalized because it's 10 point. It's 2 digits to the left of the binary point. We only want 1 digit. So we have to move it to the left, which means we're going to raise the power from 0 to 1. And our correct answer will now be 1.0 times 2 to the first power. Which, if you think about it, what is that number? 2 to the first power is 2, times 1 is 2. Hey, we got 2 over here. Isn't that what we wanted? 1 1/4 plus 3/4 is 2. So we have, this is not just a random number, that is the right answer for 1 1/4 and 3/4. Therefore, we can write the number in floating point format. Remember that the exponent will be 128. Because remember, we learned last time that we remove 127 from whatever we write. So if we're going to write 128, which is written like this, that the computer will automatically remove 127 from it and come up with the number 1. Well, that's the power we want because that's what's written over here. The exponent is 1. What's the mantissa, the number after the point? It's 0. So we're just going to write all zeros in the 23 places here. What's the sign? Well, the number is positive, so we're going to write a 0 here. And we have thus represented the number as it would be in MIPS. 0, positive number raised to the first power. The number is 1.0. Is that clear? Good. Okay. Another add example. I just added this myself a couple of days ago, just to give you a little bit more complicated example. Let's say I wanted to add these two numbers, this number and this number. So I recognize that this in scientific notation will be 1.110101 times 2 to the 7th. And this number will be 1.1001 times 2 to the 4th. I moved the decimal point 4 places to the left. I raised it 4 places. Now I've got to raise this to the same power as this one, which means I got to move the decimal place. I got to make this go up to 7. So I got to move the decimal place even more. So it's going to become 0.00110011 times 2 to the 7th. Now I've got two numbers with the same power. Now I line them up here in my columns, and I do my add. 0 and 1 is 1. 1 and 0 is 1. 0 and 0 is 0. 1 and 1 is 0, carry the 1. But I have, and again, 1 and 1 is 0, carry the 1. 1 and 1 is 0, carry the 1. 1 and 1 is 0, carry the 1. 1 and 1 is 10. And I have my number.
And for when you actually write it out, what would you write for the power?
Well, the power is still times 2 to the 7th. I haven't written the power here.
I'm saying we do.
I haven't finished yet. We haven't finished yet. It's 2 to the 7th, but this is not normalized because there's 2 digits to the left of the binary point. I only want 1 digit. So I'm going to move the decimal place. So my 2 to the 7th is now going to get a +1 to it. In other words, I kept the 2 to the 7th all along. But when I finally get my answer, I need to normalize it. So my 2 to the 7th will become 2 to the 8th. And I normalized it to 1.00. This should be the same number of zeros here. 6 zeros, 6 zeros, and then 1, 1. So now when I'd write it in MIPS, I would write, the power would be 8 plus 127, which is 135. I'd write 135 as the power. I'd write 0, 0, 0, 0, 0, 6 zeros and 2 ones, and then the rest zeros for the mantissa. And the 1 I won't write, and the sign would be 0, positive. We want to, maybe I should, let's see if I can, I don't know if it's going to do this. Control C. I don't know if it'll let me do this.
No, I think you have to select the outer part, meaning you were inside the box.
I have to go
Like, so the cursor,
like that.
yeah, that should work.
C. Control V. No, that took the inside. I don't want the inside. Whatever. I'll do it later. But basically, I'm going to take this same thing and put I'm going to put a 0 here. I'm going to put, instead of 128, I'm going to put 135, which is going to have a few more ones over here. And here I'm going to have 6 zeros and then 2 ones and then the rest zeros. Okay, that's just another example I added.
So in general, our procedure is to make the exponent of the twos the same, add them together, and then normalize the result.
Yes. In fact, yes, exactly. Normalize the result.
Normalizing the result anyways, then why do we have to make the exponents either like to the higher exponent? Why can't we go to the lower exponent?
You're right, we could. We could. But if we, yes, you're right. You're right. So if we're going to normalize it anyway, you're right. But it's just, well, it's convenient to, you're right. Theoretically, we can do it either way because we're going to normalize anyway. We have to normalize anyway. So you're right. We could do it either way. But, you know, if we have to say, let's do it, let's come up with an algorithm, we'll just show, I'm showing you the agreed upon algorithm. In other words, why do it any other way? Put it that way. This is the more likely you're going to not have, I mean, you're right. You're going to have, more likely you're going to have less normalization to do if you do it this way. You're going to have less normalization. The movement will be less in general. Because, I mean, unless you're doing subtraction, but you're basically going to have less normalization to do. Here I only have to move it 1. If I'd gone the other way, I would have had to move like 3. I would have had to move 2. Anyway, now we have to talk about overflow and underflow. Now, I may have said this slightly differently before, but we talked about how do we represent 0, and we said before that basically if the exponent is negative 127, then the value is 0. I mentioned something about the mantissa, but basically the mantissa is ignored. Once the power is negative 127, then the number is 0. In other words, once the power is 0, which 0, of course, is negative 127, because we're going to remove 127 from it. So once the power location here, go back over here, if this power is all zeros, then the number is actually 0, and we ignore what's here. Also, if the power is 255, the largest possible value in 8 bits, then we also ignore the mantissa, and we say the number is infinity. We call the number infinity. So we've already sort of thrown away those 2 powers, negative 127 and positive, negative 127 and positive 128. So we are left with a maximum power of a positive 127 and negative 126. In other words, negative 127 is gone for 0, and negative and plus 128 is gone for infinity. So that's our range of possible values. Now, the largest number we can represent is some mantissa times 2 to this power. What if, after we did this whole process and we normalized, we got a number that was, the power was 128? That could happen. If we added 2 large numbers, we're going to get an even larger number. So we could have, and if we got a power that was larger than 127, we have no way of representing it. After we've done the arithmetic and we then normalize, we can't represent it. So we would call that an overflow if the exponent is larger than 127. If the expo is smaller, because we, let's say, took a small number and we subtracted from it a large number, so the number got even smaller, and at a certain point it's going to go out of range. That's called an underflow. If the exponent, after the normalization of the exponent, so there's a third part of the steps that we got to do. We have to, after we normalize, we have to then check for overflow or underflow. Basically, we have to check our power, our exponent power. So here we have, oh, by the way, so here I just have a note about how to do subtraction. You can do subtraction the same way, basically. You just say, let's say you want to do a minus b. You can say, I can do a plus negative b. That's for sure true. And negative b, we know that we can represent in 2's complement by taking b and inverting all the bits. Every place there was a 1, put a 0. And every place there was a 0, put a 1. And then add a 1 to it. So this will give us the subtraction. So we don't have to worry about subtraction. Is essentially addition. We don't actually need a special subtraction algorithm. We just, before we do, if the number is negative, we simply invert it and add 1 and then do our normal addition. So you don't have to think about how to do subtraction as a separate process. Now, I just wanted to prove that this is true. You probably know that it's true from digital systems, but let's prove that it's true again. For example, I want to do the number 2 minus 1. I should get 1 as my result. So 2 minus 1 is 2 minus 1. That goes to, well, I have to invert this 1. Now, notice that my size of my word is 2 bits. If my size of my word would have been larger, then I wouldn't have written -1 like this. I would have written a lot of zeros here. If it was a 4-bit word, we're used to 32-bit words. But I could have a 4-bit word, then I would have to write 4 zeros here. And when I invert it, I'd have to invert all those zeros. But I don't want to write all those zeros, so I'm just going to assume a 2-bit word. So I only have to invert that 1 0. So it's a 1 0. That 0 1 becomes a 1 0. The 1 0 remains a 1 0. But I have to also add a 1 to it, so I add this 1 here. So now I've got 3 numbers to add together, and I say 0 and 0 and 1 is 1. 1 and 1 is 10. But remember, my word length is 2. So this 1 over here gets stricken through. And I do, and I'm left with 0, 1. And that, in fact, is 2 minus 1 is 1. Okay, that was just to remind you of that this is true. Now let's talk about the algorithm, which I forget who, someone mentioned. Was it Ellie? Or Eli Yosef? I don't know. Wait, is your Ellie or Eli Yosef?
Ellie.
Ellie, yeah. Because Ellie could be with an aleph.
Yeah, something like Ellie, but whatever.
They chose that spelling. Okay, given 2 floating point numbers, here's what we do. Equate the powers by increasing the power of the smaller number and moving the decimal point accordingly. So like, as you pointed out, you could do the reverse, but let's do like this. Add the numbers ignoring the power. Normalize the result to the form 1 point BBB. Why BBB? Binary digit, binary digit, binary digit, times 2 times the biased exponent. Now, I should really add another stage here, which in the book of the course in Hebrew, it didn't add, but wait, how am I going to do that? Control Z. Let's just say no. We also want to add, well, if, there might be a need to add the normalized, add the exponent that was created by the normalization. Add normalization exponent. That's what I did. That's what I did in the example too. That's why I added that example, to show you that you have to sometimes add this normalization exponent. That's what we did in this example here. That's why I showed that I had to do the 7. The whole point of this example was to show this 7.1, 7 plus 1. I need to take the original 7 and then add the normalization exponent, the 1. And once I've done that, I need to check for overflow or underflow. If yes, create an exception. In other words, you have to write. If it was a test question, you have to write. There's an underflow, there's an overflow. Then I have to do something else, which is called truncate or round the mantissa to 23 bits. We didn't yet, I don't think we discussed this yet. Yeah, we're going to discuss it now. But we have to round the mantissa because in the examples that we did up till now, always the mantissa ended with zeros. So it was fine. But sometimes the mantissa can be repeating. If you remember, we had this example where it kept going 1 0 0 1 1 1 1 0 0 1 1 0 0. It could theoretically go on forever, and yet we only can use 23. So we could either truncate it, just chop off what's outside the range of 23 bits, or we could round it. And what we're going to do is round it, actually. So I'm going to show you how to round it. Where were we? Truncate or round the mantissa to 23 bits. If we get a negative result, this is another thing we have to do. We've already know that there's no overflow or underflow, but we got a negative result. So, in other words, we got something in mashlin l'shtaim, in 2's complement. We got some kind of 1 1 1 1, you know, some negative number. So if we get a negative result, because we did, let's say, subtraction, right? If we took 1 minus 7, we're going to have a negative result. So what do? We have to convert that number into a positive number because we're not using 2's complement here. And therefore, we're going to convert the number to a positive and set the sign bit to 1, 1 indicating that the number is negative. And if there isn't that, yeah?
I think I may have missed it. When we have either overflow or underflow, do we also truncate or round the mantissa then?
It's an interesting question. I don't know, really. It doesn't really matter because once we've declared an overflow or an underflow, we've lost the number. In other words, it's a meaningless result once we have an overflow because an overflow could mean 1 bit overflowed, could mean 20 bits overflowed. So the number has lost any value to us. So I don't think there's any purpose in rounding that garbage result that we have. You see what I mean?
Okay.
Because we're not able to represent the number. Once there's an overflow or underflow, we're not able to represent it. This line 7, though, I'm not sure. Maybe one of you has an idea of it. I didn't think about it enough. But it says here, if there is a mathematical overflow, we place the overflow bit in the sign bit location. I don't know what that means, a mathematical overflow. Well, mathematical overflow is what we said over here, that the power was too large. But what's the overflow bit? Which overflow bit? There could be many. I'm not sure what he means by that, unless he means.
I think 2's complement also has overflow issues. Maybe that's what he means.
I'm not sure. It could be that you see, there's another question which I thought about, which is when we round these numbers, what if the rounding causes an overflow? It's possible. In other words, we round up. Our number is, if we truncate, we can represent the number. But if we round up, all of a sudden the number goes a little bit too high. It goes one number too high, one digit, one too high. Maybe that's what he means by this. In other words, what if?
Well, how do we know that it's only one number too high?
Because if it's rounding, then all we did was round up 1. It's like if we had 999. In other words, imagine a calculator that could only write 4 9s. You know, the largest number you could write would be 9999. But it had after the decimal point there was another 9999. So it says, oh, you better round that up Instead of being 9,999, let's round it up to 10,000. Well, now all of a sudden 10,000 I can't show on my calculator because I only have 4. I'll just get 4 zeros. The 1 overflowed. In other words, when I round up, the only overflow I'll get will be a single digit if it's a rounding error. If it's a rounding overflow. So maybe that's the single digit that we place in the sign location. Anyway, it's not that important. Just understand that if the sign bit will get the whatever the overflow is. I'll have to try to clarify that for you guys. I'm not sure what that means. I think it means what I said. Let's go on. Because now we're going to talk about rounding. And actually there are 3 different methods of rounding, but the one in bold here is the one we're going to learn because that's the one you have to know. Floating point rounding. We use rounding half away from 0, it's called. Rounding half away from 0. Here's the procedure. If the truncated fraction, in other words, we had 23 digits of our mantissa, but the mantissa is actually going on forever, so we truncate after 23. If the truncated fraction is greater than or equal to half the base, which means it's greater than, it's greater than half the base. And in this case, the base is 2, half the base would be 1. So if it's a 1, this logic applies to where the number is base 16, base 8, base 10, base 2, but we're in base 2. So if the truncated fraction is greater than or equal to half the base, which means if it's greater than or equal to 1, which means let's say it's equal to 1, then increase the last remaining digit. That's it. So we have an example. I want to just see if we have an example. I didn't do an example, but oh yeah, I do have an example. Example. Let's not talk about 23 digits because it's too much to write. Let's talk about 3 digits. Let's say our mantissa was only 3 digits, and we got the following 6 digits. So how are we going to round? Well, we look at after we want to have 1, 0, 0, and we want to truncate here, but our truncated thing starts with a 1, so it's half the base. So we have to add it. So we'll get 101. Similar, even if this number wouldn't be 101, if it would be like this, also we would get 101 because we're only going to look at this one number. We're going to add that digit, that single digit.
If that was a 0, even if there was a 1 later, we would not round up.
Exactly. If this was a 0, then we would not round up. It would be 100. All we look at is the single digit after the point of truncation. And if it's a 1, we add it to the result. So let's see another example. Let's say our example was this, 101, 100. So again, we would round up, but we would add the 1 to the 1 and get 2. So it would jump to the next column and we'd have 110. That is the rounding method. You need to know that for the exam. In other words, if you get a number that needs to be rounded, you have to know how to round it. Fine. Multiplication. So we finished addition. Let's talk about the algorithm for multiplication. Write the numbers in the float format. So, fine. Add the exponents. We're going to add the exponents. Then we're going to multiply the numbers. Then we're going to again normalize the result. And again, I wrote here, if the normalization creates a new exponent, add it to the, wait a second. We did addition. This is multiplication, but it's the same thing. Write the number normal, add the x, but here we add the exponents. Before we didn't add the exponents. Before we just left the exponents as they were. But in multiplication of numbers with exponents, the rule, you don't have to equate the exponents. You can multiply 2 to the, 10 to the 5th by times 10 to the 10th. it'll become 10 to the 15th. You add the exponents. That's the method. So you don't equate the exponents, you just add them. So they can be different. They're allowed to be different, and you just add them. And then you multiply the numbers. Well, actually, it wouldn't become 10 to the, actually 10 to the, well, let's see an example. Let's see an example. Then you round the result if needed, put the point in the right place. So let's see the example. For example, we have 5 times this ugly looking number, negative 0.4375. That's, we want to do multiplication of those two base 10 numbers, decimal numbers. But we're going to convert them now to binary. And this ugly number, actually in binary, becomes a very nice number. That's why he wrote this number. That's why we chose this number, because it looks ugly in base 10 decimal, but in binary it's actually a nice, easy to represent number. Now, if I had written 0.6667, that would be a very ugly number to write in binary. It would be very long, and it would probably never end. But this number I can easily write in binary. So let's do that. 5 becomes 101, right? 101 is 4, and 1 is 5. But I'm going to put it in scientific notation format, so it becomes 1.01. I can add a 0 here. It doesn't do me any harm. I added that just to have the same number of digits as I'm going to have over here. But actually, here I also added it. Whatever, it doesn't really matter. I added a digit here, so it's irrelevant. You can always add as many zeros as you want. So 1.010 times 2 to the second. Because I moved the decimal place 2 places, I have to change it 2 to the second. And negative 4375 becomes negative. Notice I just write a negative sign there. It's not in 2's complement. This is in regular numbers with a sign bit. That negative is the sign bit, essentially. So this is a half. Wait, this is not a half, because really the number is, this is times negative 2. So what does it mean? It means really the number is 0.0111, right? That was really the number I got. That's this representation of this. But I move the decimal point 2 places to the right, and I get this. Why is this right? Because this column is a half. I don't want a half. That would be too much. That would be 0.5 already. That's too much. So I put 1 here. That gives me a quarter. Well, a quarter is okay. 0.25. That won't push it. That's all right. 0.25. This will be an eighth, which is like, half of a quarter, 0.12, So 0.12 and 25 is 37. And then this will be a 16th. Anyway, if you add those numbers up on your calculator, you'll get this number. I'm just showing you where he got that number from. So, but I have to normalize it. So negative 1.110. Fine. So I have 2 numbers in normalized form. And the sum of the powers is negative 2 and positive 2 is 0. Now I have to do multiplication. Multiply these 2 numbers together. And what do I get? I get 1.010 times 1.11. And I say 0 times this whole thing is 0. Then I say 1 times this whole thing. Well, the 1 times 0 is 0. 1 times 1 is 1. 1 times 0 is 0. 1 times 1 is 1. So actually, if you think about it, I'm just copying this top number, which we'll call the multiplicand. That's the name of it, the multiplicand, and this is the multiplier. Bottom number is the multiplier. The top number is the multiplicand, the D at the end. So we'll take the multiplicand and we'll just copy it over, but we'll add a 0 because it's the next column. And then again, we have a 1, so we'll write again the multiplicand with another 0. And again, we have a 1. I mean, if we had a 0 here, we'd write all zeros. But of course, since we're going to add these numbers, there's no point in writing all the zeros. This line here was sort of a waste of time to write all those zeros, because there's no adding zeros to something is not going to change it in any way. So I don't even need to write it. So basically,
if it was a 1, then it could be different.
Exactly. But this number in the multiplier here is a 0. So whatever is up here doesn't matter. It's all going to come out to be 0. 0 times anything is 0. So I'm going to get a whole row of zeros no matter once I see a 1 in the multiplier. And then once I see a 1 in the multiplier, like I do in the next digit, I just take the multiplicand and cut and paste it here. But with a shift left, if you think about it. I pushed it to the left. I added a 0 to the right. And then again, the next one I see, if it would be a 0, I just would do nothing. I would just shift it left. But if it's a 1, I'm going to shift it left and add it. If it's again a 1, I'm going to shift it left and add it. So now I've got all the numbers. I add them all up, and I get my 10.001100, etc. But the thing that's interesting to notice is that whenever I have a 0 here, I basically just shift the multiplicand. And whenever I have a 1 here, not only do I shift it, but I also, before I shift it, I add it to the number. In other words, if this had been a 1, a better example would have been if this would be 101. Then I would write here exactly the multiplicand, I would write 1010. Then I'd write a row of zeros here, and then I would write this same number again. But the point is, anytime there's a 0 here, I'm just going to write a row of zeros, which have no effect on the result. So I may as well not write it. And anytime I have a 1 here, I'm just going to write the multiplicand as it is, and then I'm going to shift it. So we multiply the two numbers, we get this result. But this result is not in normalized form. So I put 1.0, I move the decimal place, and this becomes 2 to the 1. Now, as I told you before, I've got to take this 1 and add it to the sum of the powers that I already got. It just so happens in this case it's 0, so there's not much to add. But theoretically, if this would be 25, then it would become 26 because of my normalization. Now I round up, which means, assuming, remember, my numbers started with a 3-bit mantissa and a 3-bit mantissa here. So I'm going to maintain that rule. So this number, I'm not going to write it out. I mean, in other words, I'm pretending that my mantissa is not 23 bits, but only 3 bits. So this number is too long. It's 0, 0, 1, 1, 0. So I'm going to round it up, and it's going to become, I'm going to take this number and round it up. I've normalized it, and now it's 0, 0, 0, 3 zeros and a 1. So this 1 will get added to this 0, and I'll get 1.001, which is not the correct number. It's the rounded up number. That's what
I have a question quickly.
Yes.
So in step 2, we took the sum of the powers. If, for example, say the sum of the powers was not 0 and it was 3, so then the number at the end would be times 2 to the 4 because you're adding 1 to 3.
Yes.
Okay.
Exactly. That's the point that he actually left. If you look in the Hebrew book of this course, he left this point out, and I added it in because his example, just sort of worked out that you didn't have to do anything because it got a 1 there, and the 0 is still what it was. Like, in other words, you don't see the adding because you just think you just take that number and you just keep it. But really, what's going on here is I'm adding the 1 to that 0 and getting a 1. By the way, how did I know where to put this decimal point? Not decimal point, binary point. This you have to remember from your 8th grade math. So the rule is, if I have 3 here, and after the decimal point or the binary point, if I have 3, and I have, well, however many I have, if I had 2 here, I add that. So if it's 3 and 3, it's 6. If it would be 3 and 2, then it would be 5. However many places I have after the decimal point, I add them together and I count that many spaces. 3, 3, that's 6, and I put the point. That's just 8th grade math. So explanation of rounding, look at the digit after the desired precision. Add that digit to the last digit of precision. That's basically the rule. You just look at the next digit and add it. If it's a 1, add it. If it's a 0, add it. Adding 0, of course, does nothing, but I can add it. If I want a consistent algorithm, just look at the digit after the desired precision and add that digit. Okay, so that's multiplication.
Sorry. So if
Yes.
we were rounding, if we wanted, say, 4 digits after the decimal, we have a 1 there, we're adding it to a 1, so it just becomes 1.00.
If we would want 4 digits,
0010.
If we would want 4 digits, exactly, we'd have this 1, and then we would look at the next digit and see a 1. We'd add 1 and 1 and get 2, so it would become a 1 over here, and it becomes 0010. Exactly.
Okay.
If we would have a 4-digit mantissa, or 4-digit after the decimal place mantissa. I mean, I think technically the word mantissa refers to this whole number, but we're calling this number the mantissa because that's what we actually write. We ignore the 1. Okay, now let's go on. So division is same as multiplication, except in step 2, you subtract the exponents instead of adding them. If you do, in other words, if you do something to the 7th time divided by something to the 8th, it will become to the -1. You subtract them. And in step 3, you do division instead of multiplication. So that's all for this chapter. That is chapter 7. We saw how to represent a floating point in MIPS. We saw how to take 2 numbers that are, let's say, in MIPS floating point representation and multiply them together, and then stick the result back into MIPS format. We discussed briefly how to do division. We also discussed how to do addition. Okay, so let's look at chapter 8. Chapter 8 is a well, it's a related topic actually. We just did multiplication. Now we're going to look at multiplication again and show you a better way to do multiplication. Again, this was our multiplication that we did. We multiplied and we noted that every time there's a 0, we just write 0, and then we shift the multiplicand. Then if we have a 1, we write the multiplicand and shift the multiplicand. Again, if there's a 1, we write the multiplicand and shift the multiplicand. And then if there's a 0, we just write zeros and shift the multiplicand, but we're done. Once we did it 4 times, since it's 4 digits, we're done. So we ended up with this number 18, because this is 3 times 6. No, 3 times 6, yeah. 3 times 6 is 18. We got 18. If you do the columns, this is 18, 16, and 2. We can observe that whenever there is a 1 in the lower number, which I'm calling the multiplier, we copy or add the first number and shift it left. Whenever a 0 in the multiplier, we only shift left the upper number. So we could do multiplication like this. We could set a register to represent our product, set it to 0. Essentially, that's what we did. We took a register and put 0 in it. And then we added this line to it, this 0 to it. Then we added this line to it. Then we added this line to it. Each time in our loop, we added a new number to it. And when we finished our 4 times in our loop, we got this number. When we think about multiplication in binary, I'm just going to do a loop of adding the multiplicand. I'm going to add it and shift it, add it and shift it, add it and shift it. And if it's a 0, I'm just going to shift it, not add it. and then shift the upper number and move on and check the next digit of the lower number. So essentially, we're going to keep adding the, if you think about it again, that's what we do in multiplication. We add this how many times? According to what's written here, we add it. Of course, you could do it in reverse. You could call this the multiplier and call this the multiplicand. But because 3 times 6 is the same as 6 times 3. But the standard is to call the bottom number the multiplier and the top one the multiplicand. So here's the pseudocode for this algorithm that I just described. Set the sum to be 0, and then while the bottom number, or the second number, because it could be that the numbers are written left to right. But let's say while the bottom number, which we'll call the multiplier, maybe I can add that. Multiplier. So while the multiplier is still around, because actually what we're going to do is, how are we going to look at this? When we say look at the rightmost bit, what does it mean look at the rightmost bit? Look at the rightmost bit, but then shift it right. So on the next loop, this will be the rightmost bit. And then again shift it right, and this will be the rightmost bit. And then shift it right, and eventually we're going to get 0. Eventually, if we keep shifting right, the multiplier, it'll turn to 0. The multiplicand, we're going to keep shifting left as many times as we need according to the multiplier. So while the bottom number, which is the multiplier, or it's the second number, while it's still not 0, let's write that. Oh. While the multiplier does not equal 0, if the right digit, the least significant bit of the bottom number, which is the multiplier, is equal to 1, then the sum equals the sum plus the first number, the multiplicand. And then, no matter what, I only do this if it's a 1. How do I check if it's a 1? I take the multiplier and I do modulo 2 on it. If it's modulo 2, it'll give me either a 1 or a 0. So that's how I check the rightmost bit. Then, so if it's a 1, I add it. If it's not a 1, I just go to this line and I say first number or top number, however you want to call it, shift it left. In other words, the multiplicand, top number, I shift it to the left by 1 bit. And the second number, the bottom number, I shift it to the right. And then I go back again, check, is the bottom number not 0 yet? Oh, it's not 0? So do modulo 2 on it. Is it a 1? It is a 1? Oh, add it to the sum. But of course, when I'm adding to the sum now, it's a larger number because I've already shifted it left over here from the previous time. That's exactly what I'm doing here. Notice how it's shifting left each time. So here is the new algorithm. This is actually, ooh, what did I do here? Do I switch the order here? Dangerous to work on your slides while they're live. That's regular. This is the algorithm. And that's it. That's this regular. That's called the regular. Even though that's not exactly what you might have thought, that is the actual regular algorithm for. That's what you do in 3rd grade. That is the algorithm, believe it or not. Of course, it's in binary, but you do the same thing except in decimal. But that is the normal multiplication algorithm. Now we're going to talk about another algorithm. Well, it's not so new. It's 70 years old. But a man named Andrew Booth in 1950 discovered a more efficient method a more efficient method to do multiplication. And this method he looks at 2 digits instead of 1. If you think about it, over here we were looking at 1 digit. Every time we looked at 1 digit of the multiplier. If it's a 1, we add it. If it's a 0, we don't add it. If it's a 1, we add it. If it's a 0, we don't add it. We look at 1 digit. So this method is going to look at 2 digits in the multiplier. And sometimes we'll add and sometimes we'll subtract. And we'll decide whether to add or subtract based on those 2 bits. So let's take a look. If those 2 bits are 0, 0, or 1, 1, we don't add or subtract. We just shift left the multiplicand. But if those 2 bits are 0, 1, then we take the product and we add it to, we add the multiplicand to the product. This is the action to be performed on the multiplicand. What do we do with the multiplicand? We add it to the product. If it's a 1, 0, those rightmost bits of the multiplier, we subtract it from the product. And in either case, notice it says left shift 1, left shift 1, left shift 1. We always do our left shift 1 just like we always did our left shift 1 over here. And we also are going to do the right shift. These parts stay the same. But this if is different. This if is not just going to be 1, it's going to have 2 possibilities, either add or subtract. And it's not just going to look at 1 bit, it's going to look at 2 bits. That's the basic concept. Now let's see it. For the first is an important point. For the first iteration, we look at only the single rightmost bit of the multiplier. But we need 2 bits. So we're going to assume there's a 0 on its right. In other words, the first iteration, if we're going to multiply 1 times something, we're going to call 1, 1, 0. So it'll be subtract. So actually, we're going to assume a 1, so these 2 middle possibilities will never be possible on the first iteration. On the first iteration, either we just shift left or we subtract. Because, again, on the first iteration, we're going to always assume that there's a 0 to the right. So here's the algorithm in a flowchart. So what it says is like this. First of all, set the product up to 0, just like we did in the regular multiplication. Set a register to 0. Then a sub minus 1, which means bit, the bit to the right of the number that, the number has however many bits it has from bit 0 to bit n. But this is the bit minus 1. It's a fictitious bit. But we're going to set that bit to 0. This is what we said. We're going to always assume that in the first iteration, that the bit before the beginning, righter than the rightmost bit, is a 0. Set I, that's our counter, to 0. And then sign extend the multiplicand to 2n. We need to make the multiplicand bigger than it was. It'll be twice as big. So in other words, we'll see. Well, we're going to do an example with it, but we're going to make it twice as big. In other words, if you look over here, if this is my multiplicand, then it becomes this. It gets doubled in size and gets zeros to the left if it's a positive number. So sign extend the multiplicand to 2n. Now wait, let's remind ourselves, the multiplier is the second number. So the multiplicand is the first number. So that's this number, exactly. So this number, are going to get these zeros over. Now, what do? I check those 2 bits. This is A, that's the number sub 1, and this is the number sub I minus 1, which means that this is the first digit, and this is the digit before the first digit, which on the first iteration is set to 0. Now, notice this is I, and I starts out at 0. But I is going to go I plus plus over here. So it's going to go up to 1, and then this will be checking bits number 1 and bits number 0. It'll keep moving leftward. So if the rightmost bits are 0, 1, product equals product plus multiplicand. If the rightmost bits are 1, 0, equals product minus the multiplicand. If it's neither of those possibilities, which means either it's 0, 0, or 1, 1, then don't add or don't subtract. But in all four cases, go to this box, right? Notice the arrow keeps going here and here. In all four cases, after you've added the number, shift left the multiplicand by one space. So the multiplicand will get larger. Then check, is I equal to n minus 1? If there's two digits in the number, and we've done this twice, we're done. Right? Now there's n starts at 0, then it goes up to 1. 1 equals 2 minus 1. So we're done after 2 times.
How does this work? Like, it seems like just like such like a random
It
collection
does
of
seem
things
like
to do to get to multiplication.
well, we do notice a certain similarity that we're left shifting the multiplicand, which is making it bigger, and we're adding it. That sounds right. The subtraction is the funny part. You're right. How does it work? You have to have a greater mind than I to really see it, but we are going to prove it mathematically that it works. That is one of the things we have to do. Prove it
Will this
mathematically.
algorithm also work in decimal or only in binary?
It's going to only work in binary because we're looking at
if it's 0, 1, or
if it's 0, 1. We'd have to have 100 possibilities if it would be addition. If it would be decimal numbers, right? Yeah, it's only going to work in binary, which gives us 4 possibilities. So fine. So this will only work in binary. Yeah, binary has this unique property, which is that you either have a 1 or a 0. Either you copy the multiplicand or you ignore the multiplicand. As opposed to regular numbers like 7 times 3, you don't copy, you do multiplication. You know what I mean? There's no multiplication here. And that's kind of the clever thing here. We're doing multiplication, but since we recognize that the numbers are stored in the computer always in binary, whatever number, when he wants to do 7 times 5, it's really going to get converted to binary, and we're going to multiply 7 binary times 5 binary, which means we can use this method always. So all multiplication will actually be Booth multiplication.
Are you going to show us an example of how this is done?
Yes, I will.
Okay, cool.
So I keep going until I'm done. That's the flow chart. The flow chart, really sit on and make sure you understand it. That is the whole concept. It's right there. Now let's do an example with Booth algorithm for multiplication. Given an expression xy, we'll call x the multiplier. In Hebrew, it's called a kofel. The x is the multiplier and y the multiplicand. So let's say we want to multiply 6 times 3. So we have 6 times 3. We added some leading zeros just to make it a multiple of 4, multiple of 2. So it should be 3 digits, but not necessary. But let's do it that way. So first, let's make a product of twice as many bits as what we've got. We had 4, so let's have 8. 1 byte. 8 bits of zeros. Remember, we set the product to 0. Now take the multiplier. Now take the multiplier, which is the first number, the 6th, and extend it to the size. Wait, is it the multiplier? Right. Yes. And extend it to the size. Is that what I said before? I'm just checking.
Earlier you said the multiplicand was the first one, and the multiplier was the second one.
Shouldn't matter though.
It doesn't matter. Whatever. I guess it's semantics, but.
Yeah, this is wrong. See, what I did here was the slide is correct. It's that my additions to this slide are problematic. Let's just get rid of it. Just confuse you. Okay, so we take the multiplier, the first number. Now take the multiplier, the first number, and extend it to the size of the product by adding zeros to the left. So that was the multiplier. We added our zeros, and our multiplier looks good. Now we go on. Now we are ready to start the loop. We want to look at bits a of I and a of I minus 1 of the multiplier. Remember, this is the multiplier. So we want to look at this 0 and the assumed 0 on the right of it. But we can't just assume things in algorithms. So how are we going to actually, we need to put a 0 there. So how do we do that? We're just going to take the multiplier and shift it left. In other words, we're going to take this multiplier and shift it 1 to the left. Well, that's going to insert a 0 there. So this gives us 0, 0, 0, 1, 1, 0, 0. We only do this on the first iteration. Since the right two bits of the multiplier are now 0, 0, we are going to shift left the product, shift left the multiplicand. In other words, according to this algorithm, if we have 0, 0, we don't add or subtract. All we do is shift left the multiplicand. So let's do that. So we're going to shift left the multiplicand. What is the multiplicand? The multiplicand is this 0, 0, 1, 1. So we're going to shift left the multiplicand, and we're going to get instead of 0, 0, 1, 1, we're going to get 0, 0, 1, 1, 0, and neither subtract nor add it to the product. Now shift right the multiplier. In other words, we were looking at these two bits of the multiplier, but now we want to look at the next two bits of the multiplier. So we have to shift it right and lose that 0 and just have 1, 0 now. So we're going to shift right. Now shift right the multiplier and examine the right two bits. And we're going to keep on shifting right the multiplier. We're never going to shift it left again. Just that was the first time we did that. Now shift right the multiplier and examine the right two bits. They are, in this case, 1, 0. So we have to do what it says in our algorithm. If it's 1, 0, subtract product minus the multiplicand. So they're 1, 0. So we subtract the multiplicand from the product. Remember, the product was 0. We put zeros into the product because we just started out and we hadn't touched it yet. So the first thing we do is this 1, 0 is minus. So we take all these zeros minus our number, our multiplicand, after it already shifted once. And following the rules of 2's complement, we note that we can add the negative of the second number. When we add, how do we add? Well, we invert this and add 1 to it. So it becomes 1, 1, 1, 1, 1, 0, 0, 1. But we add a 1 to that, and 1 and 1 is 10. So we get 1, 1, 1, 1, 1, 0, 1, 0. That is the negative of this number. This is actually 6. So that's negative 6. And we add negative 6 to 0, and we get negative 6. You know the joke? There are 10 kinds of people. Those who understand binary math and those who don't. I guess I told you that joke before.
We're all laughing, just we're on mute.
Ah, okay. So I'll wait a few seconds for you to finish laughing and then we'll go on. Okay, so 1, 1, 1, 1. So right, 1 and 1 is 10. So we got this number. This number is absolutely meaningless. It's not what we want. It's actually negative 6. We don't want negative 6. So we have a positive number, right? We have to have a positive number. So fortunately, we're not done. Loop continued. Now, as in step 2, we shift left the multiplicand. Remember, the multiplicand had been 0, 0, 0, 1, 1, 0. We're going to shift it left now again, because we always shift it left. And we get 1, 1 with 2 zeros now. It was 6, now it's 12. Next, we right shift the multiplier, because we're always right shifting the multiplier. And remember, we had 0, we had 0, 1 before. Here's the multiplier. We had, where's the multiplier? Here. We shifted it. We started off with 0, 0. Then we shifted it right. We got 1, 0. Now we're going to shift it right again. And we're going to get 1, 1. So we shift right the multiplier and examine the rightmost bits. These bits are 1, 1. So 1, 1, according to our algorithm, is do nothing. Just shift left, the multiplicand. So 1, 1, we shift left. So where are we? Again, we shift the multiply. Where were we? These bits are 1, 1, so we do nothing except shift left multiplicand, and the multiplicand goes up from 12 to 24 now. That multiplicand is getting very large, but it's okay. Again, we right shift the multiplier and examine its rightmost bits. Now we're in the next loop. They are 0, 1. That's, by the way, the last one that we're going to have in the multiplier. The multiplier has been shifted. You know, this number has been shifted to the point where now we're just looking at this 0 and this 1. From now on, the next time we're going to just look at zeros, and that means we're done. So we're about to be done. So they're 1, 0. So according to our table here, sorry, 0, 1. 0, 1 is add. So we go over here. They are 0, 1. So we add the multiplicand to the product as on the right. And we take our -6 and we add to it 24. Well, what's -6 and 24? 18. Notice the 1 gets chopped off because of our frame, because we're talking about an 8-bit frame. We could continue shifting the multiplicand left and the multiplier right forever. But the multiplier becomes all zeros. So even if we do this, we'll just keep getting 0, 0, 0. We'll keep just shifting the multiplicand left, but never adding it. So we'd have an infinite loop. But, you know, we're going to count. Anyway, what we've seen now that the multiplier has become all zeros, so we're done. Also, we can say that if we had an I counter, we would have reached n minus 1. So that's it. That's it as far as the Booth algorithm. There is a homework assignment. I think it's, I don't know, I think it's 5, but I didn't translate it yet. I'll translate it for you, where you're going to have to do some Booth multiplications. All right, we'll stop here. It's confusing. If you're confused a little bit, go over it again. Try a different example. Take 2 other numbers, not too big, but take 2 other numbers and try it out, see if you can do it. Okay, guys. Good luck. Laila Tov.
Thank you.
Thank you.
Sure. You're
All
welcome.
right. Thank you.
Sure.
Mm.
Bye.